Okay, let's dive into this. We're looking at a true classic in neural networks, the rectified linear unit, or ReLU. It's been fundamental for years, but it comes with a well-known problem, the dying ReLU.
It really is remarkable how enduring ReLU is, and yet this challenge, it's just persisted. It represents a core difficulty in keeping all parts of a network, well, actively learning.
Absolutely. And you've shared some fascinating source material with us, centered around a paper titled The Resurrection of the ReLU.
Mm.
Our mission for this deep dive is basically to unpack this research, pull out the most important insights, and really understand how this new method aims to, well, revitalize ReLU and improve performance.
Right. We want to focus on understanding the mechanism behind this approach, what the experimental findings reveal, and, what makes it effective according to the paper.
So thinking back to ReLU's rise, it became really prominent with landmark models like AlexNet, didn't it?
It did. It brought real advantages over older activation functions like TAN, things like significantly speeding up training convergence.
Which is huge.
Oh, definitely. And improving how models generalize to new data, a big part of its appeal was just its sheer simplicity and also its inherent sparsity.
Sparsity. How does that work?
Well, by setting any negative input to 0, it naturally silences some neurons. This can be efficient computationally, and it encourages the network to rely on different subsets of neurons for different inputs. There are also some interesting ways to view its decision boundaries geometrically, sort of relating them to concepts of folding space. It's quite elegant in theory.
But the key issue, as you mentioned, is this dying ReLU problem. This happens when a neuron consistently gets negative inputs during training, so its output is always 0.
And critically, the gradient flowing back through it during learning is also 0.
So it just gets stuck. It can't learn any further updates.
Yeah. Right. It essentially becomes inactive, unable to contribute anymore. And this limits the network's capacity because, well, some units are just permanently offline. This challenge motivated the development of many alternatives over the years. You've probably heard of some, like leaky ReLU, prevailing, GELU, SELU, SiLU, or ELU.
Yeah, those functions typically try to fix it by introducing some non-zero behavior for negative inputs, right? Trying to avoid that zero gradient cliff.
That's the usual approach. But the paper you share proposes a different path forward, something called sugar.
Sugar, surrogate gradient learning for ReLU.
Okay, the core idea of sugar is quite clever, actually. It preserves the standard ReLU function during the forward pass. So the network behaves just like a normal ReLU network when it's making predictions.
Okay, same output behavior.
But during the backward pass, when gradients are calculated for learning, it replaces ReLU's zero derivative for negative inputs with a smooth, non-zero surrogate derivative.
So you keep the forward pass benefits, maybe like that sparsity, but you sidestep the zero gradient issue on the backward pass. The paper explains this is done using a technique called forward gradient injection, FGI.
Exactly, FGI. It's an idea adapted from research in spiking neural networks, interestingly enough.
How does that work conceptually?
Conceptually, FGI uses a mechanism you might see it in coding frameworks as a stop gradient operation to sort of interrupt the normal backward flow where the gradient would be 0. Instead of letting it be 0, it injects the gradient from a different, specifically designed function, the surrogate, just for that backward pass calculation.
So it allows gradient information to flow back even when the original ReLU function was flat, or technically non-differentiable right at 0.
Right. It's like telling the training process, okay, ignore the actual 0 slope here, use this engineered slope instead to figure out how to update the weights.
And to do this, they needed specific surrogate functions for that injected gradient. The paper introduces 2 new ones, SiLU and NeLU.
Let's start with SiLU. It's designed drawing inspiration from functions like SiLU, which has self-gating properties, and also the smoothness you see in GELU. It's described as a bounded sigmoid linear unit. Basically, its gradient curve for negative inputs is smooth and limited, and there's a tunable parameter setting its effective lower bound.
Okay, so inspired by SiLU and GELU and NeLU.
NeLU is conceptually a bit simpler. For positive inputs, its gradient is just 1, like standard ReLU. But for negative inputs, it introduces a smooth negative slope, again taking a cue from GELU. It also includes a parameter, alpha, that lets you control the magnitude of this negative gradient, which the paper suggests helps keep training stable. They have figures showing how these surrogate derivatives look compared to vanilla ReLU's sharp step.
Makes sense. And the research then goes into quite extensive experiments comparing these sugar-enhanced ReLUs against standard activation functions.
Yes, across different network architectures and datasets, they primarily focused on VGG-16 and ResNet-18 using the CIFAR-10 and CIFAR-100 image classification benchmarks. Those are pretty standard tests.
And what did they find? Did sugar make a difference?
A significant difference, according to the results presented, especially in generalization performance, how well the model performs on unseen data. Sugar with the SiLU surrogate seemed particularly effective in these tests.
Can you give an example?
Sure. On CIFAR 100 with a VGG-16 network, vanilla ReLU got around 48.7% accuracy, but sugar with SiLU boosted that quite dramatically up to over 64.4%.
Oh, that's a big jump.
It is. And with ResNet-18 on CIFAR 10, accuracy went from about 76.8% for standard ReLU to over 86.4% with sugar SiLU. The paper notes that other functions like ELU and SELU also saw reliable gains when used with sugar. The tables really lay out the full picture.
Did all surrogates work equally well?
Not in this setup. They mentioned that leaky ReLU and their proposed NELU showed sort of negligible or even slightly negative effects when paired with the sugar on VGG and ResNet. SiLU was the clear winner there.
We also had that controlled experiment, right? The one designed specifically to cause dying ReLUs.
Yes, using a setup from some prior research. And this really highlighted sugar's ability to prevent units from dying. Using sugar with SiLU significantly reduced the number of dead neurons compared to standard ReLU in that test. It even allowed networks to solve regression tasks that the vanilla ReLU networks completely failed at because too many units had died.
So it demonstrably keeps neurons alive and learning.
Yes, the paper shows it increased the average activation probabilities across the layers.
Now, what I found really interesting was the evaluation on more modern architectures, things like Conv2NeXt and Swin Transformer, which usually use GELU, not ReLU.
Yes, that's a critical test. How does this resurrected ReLU stack up against the current defaults? And here, sugar this time, specifically paired with the NELU surrogate, proved competitive. In some cases, it even slightly surpassed the performance of the standard GELU base models.
Really? Even against GELU?
According to their results, yes. For Conv2NeXt, the GELU base achieved 83.74% accuracy, while sugar NELU reached 83.95%. With the Swin Transformer, sugar NELU got 61.48% compared to GELU's 61.39%.
That's fascinating. So NELU worked better here, unlike in the VGG-Z tests.
That's what they found. They did note that SiLU actually performed slightly worse than the baseline GELU in the Swin Transformer case. So the choice of surrogate seems important depending on the architecture.
Still, seeing a ReLU-based approach, using this gradient trick, compete or slightly edge out GELU in these modern networks, that's quite a statement.
It does suggest that maybe relying on those inherently smooth activation functions isn't the only path, or perhaps always the best path for top performance.
So the paper delves into why sugar seems to work so well. What's the analysis show?
They looked at a couple of things. One was the distribution of neuron activations across the layers in VGG-16.
And what changed with sugar?
It showed a pretty clear shift. In the deeper layers, where vanilla ReLU often had many neurons that were either always off, dead, or almost always on, sugar SiLU resulted in a much more balanced distribution, more neurons firing moderately.
Suggesting it kept those deeper neurons actually engaged in contributing.
Precisely. And interestingly, in the earlier layers, the sugar model showed slightly more sparse activations, more selective firing.
So a balance, keeping deeper neurons active while encouraging more specific responses early on.
That seems to be the interpretation, that this balance is beneficial for generalization.
They also looked at the loss landscape, didn't they? Visualizing the error surface.
Yes, around the trained network weights. This analysis indicated that sugar, particularly with SiLU, again in this VGG context, creates a smoother optimization surface compared to training with vanilla ReLU.
Smoother meaning fewer sharp bumps and valleys. Easier to find a good minimum.
Kind of. A smoother landscape where the loss doesn't change quite so drastically if you nudge the weights slightly suggests better behaved, more predictable gradients during training.
Which helps explain why they also observed faster convergence sometimes, as mentioned in the paper.
It all connects. The smoother landscape implies better conditioned gradients, leading to more stable and potentially faster learning.
And the paper frames sugar itself as a kind of regularization technique.
Yeah, that's an interesting perspective they offer. Unlike standard weight decay, which just penalizes large weights uniformly, sugar adaptively modulates the gradients based on the neuron's state specifically, whether it's in that negative region where it might die.
And this choice of the surrogate function SiLU versus NELU ties into this regularization idea.
It seems so. The thinking goes, in networks that don't already have a ton of built-in regularization, like the older VGG or ResNet architectures, a surrogate that makes a bigger change to the gradient behavior, like BSLU, provides a helpful dose of effective regularization. This aids generalization.
Okay, so SiLU acts as stronger regularization there.
But in highly regularized modern networks like Conv2NeXt and Swin Transformer, which already have sophisticated regularization built in, a surrogate that stays closer to ReLU's original behavior, like NELU, works better.
Why is that?
Because it provides just enough gradient flow for those negative inputs to prevent dying units without messing too much with the network's existing carefully tuned regularization mechanisms. Using BSLU, there might be too much regularization, potentially leading to underfitting. NELU offers a lighter touch.
That makes sense. Matching the surrogate's behavior to the network's existing characteristics. So, wrapping this up based on the source material, the main conclusion seems pretty clear. Adding this surrogate gradient learning sugar to classical ReLUs makes them powerful competitors again.
Yes, it really seems to revitalize them. The evidence suggests it enables more robust training dynamics, significantly improves generalization, and directly tackles that long-standing dying ReLU problem.
While still keeping some of the benefits like sparsity.
Exactly. It keeps the forward pass behavior, which might be why some beneficial properties are retained.
This research really challenges the notion that you have to move to GELU or swish or other complex functions to get top-tier performance. It suggests there's still a lot of potential in ReLU if you just handle its gradient more carefully.
It definitely raises an interesting question about necessity versus optimization.
So what does this all mean going forward? The study focused heavily on image classification tasks, right?
That's true. Mostly CFAR and ImageNet were mentioned in the context of the transformer results. It naturally makes you wonder, how well would sugar perform in other areas?
Like natural language processing, maybe? Or time series data? The dynamics of activations and network architectures can be quite different there.
Or even thinking about efficiency, could the sparsity potentially maintained by sugar ReLUs make them particularly useful in resource-constrained settings, like on mobile devices? Something to consider.